And hi, welcome back. So today we're going to continue the substitution process that we were doing in the last video. So we're going to non-dimensionalize this equation. Yeah, house party. Okay, never mind. Yes, we're going to non-dimensionalize this equation. And this is how we're going to do it. Remember before we wanted to use U star, right? U star, which is the tau at the wall divided by the density, and then we square root it, and then the relevant length scale will be this nu over U star. Okay, so I'll just call this Y star just for the sake of consistency. So let's just divide throughout by U star. Let's just divide throughout by U star. U star. Okay, and by dividing throughout by U star, we can get 1 over U star here, and I can change the U bar into U plus. Okay. I'm not going to do the differentiation steps. Hopefully you know what I'm talking about. Okay. Okay, never mind. I'll do it anyway. So U star U plus is equals to it's not D, it's U bar divided by U star. Okay, given that U star is a constant, we find that du plus equals to du bar times 1 over U star. Okay, so that's it. So now the second step is to multiply both sides by this characteristic length scale so that we can do the same for the bottom. Of course, technically speaking, you want to divide the denominator by this characteristic length scale, but doing that would effectively mean multiplication. So we'll do the same thing. We'll multiply Y star to both sides, which is over here, and we can change the denominator to Y plus. So what we have left on this this side, it is Y star over U star. And what is Y star? Y star is just nu over U star. So we can just copy that down. So nu over U star. Okay. Okay, there we go. And we can just do a U star square at the bottom, and we'll just have nu at the top. Okay, so if we divide both sides by nu, we will just get 1 nu t over nu. Then we'll have this, and that is what our non-dimensionalization results in. And what might you ask is this U star? Well, we have to go back, and we realize that nu star is the square root of tau wall over rho. So noting U star equals to tau wall over rho, we'll just have this at the bottom. Okay, and by that we can just get rid of this. Okay, we can cancel the rows, and that's what we get. And okay, so that's how we substitute our equation. Of course, assuming rho is constant for incompressible fluid, which is the subject of what I'm talking about here. I'm not going to deal with compressible flows like for airlines, but airfoils. But this is for incompressible flow. Make things simple, and if you're doing that kind of application, yeah, it's just for those applications. So okay, so pretty much we are set, almost ready to solve. We are almost ready, except for one small problem. If you see on the left hand side, we have this ratio of the apparent shear stress over the wall shear stress. Okay, yeah, the apparent shear stress over wall shear stress, and that makes it a little bit more difficult to do curve fitting or data fitting. Okay, because we don't know what the gradient of u plus over y plus is, as long as we don't know this. This is a big unknown, and that is something we'll need to deal with. So let's make an assumption. Considering the boundary layer. Okay, so for the boundary layer, means over here, we can assume, okay, we just assume this, okay, tau wall is much greater than tau turbulent, meaning to say that the wall shear stress is much greater than the turbulent shear stress, which means that, okay, this means that tau apparent is approximately equal to tau wall, because the effect of turbulent shear stress compared to everything, it is not very big. So the contribution from turbulent shear stress is small in the boundary layer, and therefore we can assume that this tau apparent is constant and it's almost equal to tau wall. So that's one of the assumptions that can be made. So we can assume tau apparent approximately constant and approximately equals to tau wall in the boundary layer region, close to the wall. And this is one of Prandtl's assumptions. Okay, so that makes things a lot easier. Makes the left side 1. And now, by and large, we can simplify this part as well. Okay, so we have a simpler kind of equation, and now we can separate into two regimes. Okay, so even in the boundary layer, there are two regimes. Okay, one regime is where nu much more than ut. Okay, so this means that there is zero turbulence inside this layer. This is called the viscous sublayer. Okay, so that's what we were kind of talking about earlier, but we have not clearly defined. So when this is true, we are in the viscous sublayer regime. So we will have du plus dy plus equals to 1. And that is a very simple form of the equation. But we have a second regime that we did not discuss before. We have nu t much more than nu. This is what we call the fully turbulent sublayer. Okay. Now yes, anyway, for this one, we will be able to put this here, and we'll take out the 1, where nu t is much greater than nu, so that this highlighted value here nu t over nu is much greater than 1. So we will have some form of equation like so. The problem, of course, is now how do we determine this nu t value? Now that one I'll cover in a while. Let's deal with the easier problem first, the viscous sublayer. So if we were to integrate this equation and assume that u plus only depends on y plus, okay, so if we fix everything else, so we have this u plus equals to, if we integrate this becomes y plus some constant. So we're going to need a boundary condition. We need a boundary condition. And that's easy because at u plus equals to 0, y plus equals to 0, that means we are at the wall. U plus equals to 0. This is the no slip condition. We just put it in non-dimensional coordinates here. But this is when u plus equals 0, or when u equals to 0, u plus equals to 0. And when y equals to 0, y plus equals to 0. So this is essentially our no slip condition. So C is equals to 0. And this is the equation for the viscous sublayer. Okay. Viscous sublayer equation. Okay. No problem. Yeah. Now we need to take a look at regime 2, which is the fully turbulent sublayer. This is slightly more difficult to deal with than, say, the viscous sublayer, because here it's just a laminar regime. We don't have to deal with turbulence. Over here we have to deal with turbulence. So how do we deal with this turbulence? So the first thing to do to try and find out this turbulent viscosity is to recall how we got it in the first place. Okay, so if we remember, we have this term minus minus the average after we do some averaging. Remember, this was our closure problem in the first place. So u prime v prime equals to nu t into partial u bar partial y. Okay, so this is inside the boundary layer. And so remember, this was our closure problem. So to try and find out what nu t is, we have to try and estimate what this value is. So we can do order of magnitude estimate for this quantity. Oopsie, I'll just copy and paste this here. And what is this order of magnitude estimate value for this u prime v prime for our closure problem? This was actually described by Prandtl. This estimate was described by Prandtl in something called the Prandtl's mixing length model. So what is the mixing length model? So just imagine with me a while. You are somewhere near the wall. You're somewhere near the wall, and there are, packets of fluid floating around this place. Okay. All right. So, I mean, truthfully, the fluid itself, it's basically made up of packets of molecules. If you think about water, you can think of it as water molecules swishing over the place because there's turbulence. But if you take a look, okay, we don't have water molecules, let's say moving independently of each other. So we can think of it like that. So these x's are the small water molecules. Okay. So we don't really have the small water molecules sliding past each other so often, all the time. Or we don't just have that. We sometimes have water molecules, if it's a water is the fluid or some other kinds of fluid, they can travel as a cluster. They can travel as a cluster. Okay, so water molecules or fluid particles or fluid atoms can travel together as a cluster. Okay, so yeah, but of course, as this cluster isn't always very stable, so if you have a fluid cluster or fluid ball, if you have a fluid ball going from, let's say, point A to point B, okay, somewhere along the path, the fluid ball will start to split up, because of course there are forces that can cause the fluid ball to split up or join with other fluid balls, and that's just what happens in the fluid. They can travel together as a cluster for a very short period of time. After that, they will start to split, either split or change form or join with other fluid clusters, etc., etc. And what is the mixing length? Well, the mixing length is the average distance this fluid cluster can travel before it changes, it splits apart or joins together with other clusters, etc., etc. So this length where this cluster can travel, that is the mixing length. So what does mixing length have to do with the fluctuating part of the velocity, for example, u prime or v prime? So, well, let's have a estimate, right? So this is a fluctuation, right? It's a fluctuation, and what is this is the velocity fluctuation, and what is the scale of fluctuations in this situation? Well, if you have a velocity 1 here and a velocity 2 here, the size of this fluctuations of the mean velocity is u2 bar minus u1 bar, right? So this is the size of the fluctuation. Okay, so this is the fluctuation size. Okay, this is the size of the fluctuation, and this will be on the order of magnitude similar to u prime. Okay, so how do we so this is the largest fluctuation we can see in the system based on the mean velocities. And then this is the unfiltered or the residual velocity. This is the turbulence part. Okay, so we are also making this assumption, okay, that the mean velocity fluctuation is on the order of the turbulent velocity fluctuation. So where does the mixing length will come in over here? Okay, let's put this down. Oops, let's put this down here. Pull this out, and yeah. So since we have this, right, let's use purple. u2 bar minus u1 bar and we have this mixing length. Remember, this is the mixing length. Okay, so u2 bar, u1 bar minus u2 bar over the mixing length. So we use this mixing length to divide both sides through. Okay, u prime over L. Okay, and what we can do is to express the left hand side as simply del u bar del whatever the length scale is, for example y. Okay, so this is some sort of velocity gradient, and this will be equal to u prime by L. So again, where did we come from? We started with saying, okay, we are trying to estimate the biggest fluctuation, right? The biggest fluctuation between the biggest fluctuation in velocity within this mixing length scale is this much, u2 bar minus u1 bar. And that will be the metric we use to estimate our turbulent velocity fluctuation. They should be on the same scale. Now, since the region of interest is within the scale of this mixing length, L, we can divide L by both sides. And then we can say, oh, this thing in the box here, it's actually a velocity gradient. And we'll get this velocity gradient here equals to u prime over L. And we can finally get u prime equals to some mixing length del u del y. And a similar argument, at least conceptually, if the turbulence is isotropic, we can also make the same argument there. Okay, so let's write this down. This is a very rough conceptual explanation. It's not fully accurate, but it tries to trying to like give you an idea of where this comes from. So the max fluctuation within some mixing length L. Okay, I won't do that. Say let's visualize fluid motion in turbulence. Usually they come in the form of eddies. Okay, so sort of we can visualize the eddies or fluid yeah. Let's see. Yeah, when you see eddies going around in the fluid, so when you see eddies in the fluid motion, we can assume that okay, these eddies must be actually flow. I mean, a packet. It's like, you know, you have these fluid globules going around in a circle. So these are the fluid balls we are talking about in the mixing length. Think of eddies being balls of fluid going round in circles. So that's one way of thinking of eddies. And the maximum distance this ball travels on average without disintegrating is the mixing length L. Okay, what is the biggest velocity fluctuation within this mixing length? So this will be u bar 2 minus u bar 1. and this will be approximately equals to the, at least on the order of magnitude basis, it's approximately equals to the turbulent part of the velocity. So if we divide both by L, we divide both by L, both sides by L, we can see that the right hand side is basically just the gradient, velocity gradient. Okay, and of course the same can be said for the y side velocity in the boundary layer, v prime by L. And why is this disintegration thing important? It is because, okay, if your the fluctuating part of the velocity is so big within this what do you call that, ball, okay, let's see, if we have a fluid ball and the fluctuating part of the velocity is so big, so let's say this is u prime, if the u prime is too big, we will get disintegration. Okay, disintegration. Okay, so if the u prime is too big for this ball, we will have a disintegration effect. So then we cannot estimate this u prime. But assuming that u prime is not too big, the fluctuating part of the turbulent velocity is not too big, and this ball manages to stay together, then we are able to find an estimate of u prime. So this whole thing, mixing length hypothesis, only holds true. So this, okay, you see this law here only holds true if the ball doesn't disintegrate. So the ball not disintegrating will give you the first part here, right? So, and what's the length of the ball not disintegrating? This is L. Okay. So again, let me repeat. The ball not disintegrating will allow you to estimate u prime as being on the same scale of this change in the mean velocity. Because if the u prime is too big, the ball will disintegrate. So we have no way of estimating u prime. So to estimate u prime, we need to assume that the ball doesn't disintegrate. That's why you can say u2 prime minus u1 prime equals to, u2 bar minus u1 bar equals to u prime. So that's what assuming that the fluid ball doesn't disintegrate, it allows you to make this kind of equation. So we have this mixing, but of course the ball eventually in the turbulent flow will disintegrate. So we need to narrow down our scope. This ball does not disintegrate within some mixing length L. So we put that down. We say that the length scale of this ball, fluid ball existing, is L. So we can just use this L and divide throughout by both sides. And then we'll get this, which we can equate as a velocity gradient, which is very convenient for us since this is what the bulk fluid property is. And we can find u prime in terms of some mixing length L. Of course, if you have a longer mixing length, it means that the allowed u prime is a lot bigger. All right. So okay, so hopefully that gives you some intuition to it. It may not be 100% correct, but at least it helps you give some sense to the maths and not just plugging random numbers together. All right. So and going from here to here, we can sort of assume the turbulence is somewhat isotropic, because the u prime and the v prime doesn't really matter which direction, it's all random, so that the velocity fluctuations in the x direction is pretty much on the same order of magnitude as the velocity fluctuation in the y direction. So hopefully now it is clear where these things actually come from, why the fluid ball going through the fluid will result in this kind of equation. It gives some rough idea, yeah, and how we can say this u2 bar minus u1 bar equals to u prime. So yeah, so this dividing by L will give you the velocity gradient, which we can then plug back into our equation. So now that we have this u prime and v prime, we can multiply them together. U prime, v prime, divide by L squared equals to, okay, so we just multiply these two equations together. We have du bar dy, or partial u bar partial y squared. Okay, and then I mean, if we can get the order of magnitude like such, u prime v prime equals to minus, rather I can put this minus on this side, equals to, alright, so the minus sign is just to make it consistent, but I just ignore all the signs before to give you an order of magnitude estimate. So I mean, here the more important thing is order of magnitude. So it will be L squared into partial u partial y squared. Now we also realize that, oh okay, we can relate this to nu t into partial u partial y, because this is what our closure turbulent viscosity model is. So now what we have is that if we compare the equation, nu t equals to L squared into du dy, or partial u partial y. This is the basic mixing length model. Hopefully you try and get the gist of what I'm talking about here. It can get a little bit confusing with the whole ball not mixing, I mean not disintegrating and all that, but having that ball not mixing, it allows you to get an estimate of this, which you otherwise won't know, as a function of this the velocity gradient. Otherwise it's impossible to know. So this is an order of magnitude estimate based on the assumption that fluid balls can flow through the fluid in a turbulent flow without disintegrating. Then you can make this order of magnitude estimate. Therefore, based on this mixing length model, this turbulent viscosity will be L squared into du dy, or partial u bar partial y. So okay, great. That's what mixing length model is. But you still have to guess what this L squared is, or L is, in order to plug it back to solve this equation. So in fact, you have this turbulent viscosity here, which you must put in terms of y plus. So for, okay, I'll just get that out of the way. For L squared, L, okay, for L, we need this in terms of y plus. How? So that's a topic for the next video. Thanks for watching. I'll see you guys again. Hopefully, if you found this helpful, please leave a like and subscribe. Thank you very much. I'll see you again. Bye bye.